Okay, so today we are looking at simplifying square roots. Okay, or simplifying radicals. We used to do a ton with square roots. It used to be a standard that we did a lot with square roots. Most of that has come off the table, and we are going to do very minimal with square roots. Guys, headphones need to be out, devices need to be put away. We are going to be doing enough so that we understand the square roots that are coming up for our next unit, which is actually solving quadratics. So radicals is not a unit. Okay, there are just going to be square roots involved in some of the other problems that we look at for our next unit. So we need to know what to do with that. All right. I hope at this point we understand a couple things, like the square root of 25 is 5. Because 5 times 5 is 25. Even if it's a larger perfect square, like the square root of 256, right, you could put that in your calculator and it would tell you 16. Okay? The problem is that anything that is not a perfect square, if you remember way back when to the beginning of Algebra 1, anything that's not a perfect square is an irrational number. Okay, and an irrational number is a number like pi that literally never ends. There is no repeat, there is no pattern, there is no nothing. It goes on for forever. Okay, so there's like a computer at NASA that has been like calculating the digits of pi for like, I don't even know how many years straight at this point, and has found no pattern, no nothing.
Like just every single day.
24 hours a day, digit after digit after digit after digit after digit after digit for like 20 some years, and no repeat, no pattern, no nothing. Yes?
How many digits does it find a day?
I don't know the answer to that. But I mean, we're talking like people have calculated billions and billions of digits, and we have not found any type of repeating pattern in it. Right, because at first the idea was like, maybe the repeating pattern is so long, we're not seeing it.
Isn't NASA like a space?
You know?
This is what
Then how did pi come to exist? Okay, so here is where pi came from. So you probably know, or at least remember, in middle school when you were learning about like area formulas and perimeter formulas.
I remember I used to think that stuff was so hard.
Okay, we learned that the area of a circle is pi r squared, and the circumference is sort of like the perimeter. Amelta, can you please just close your computer all the way? Okay, circumference is the distance around. Okay, is 2 pi r or pi d?
Wait, what?
2r, 2 times r, right? A radius is this distance. The diameter is all the way across.
I read you.
Okay. And what they found is when they were looking at this distance of a circle, like if they measured this with a ruler, and they measured this distance around with a ruler, they found this weird ratio of numbers that they couldn't like write down. Right? They tried to like start dividing it out and figure it out, and it was this big long repeating decimal. And that is where pi came from. Okay, but the idea was, as we got more advanced with technology, that maybe if we had a computer, right, who could look for like a repeating pattern that's 1,000,000 digits long, maybe we would find it's actually a repeating decimal. It's just so long of a decimal that's repeating that we're not noticing it when we look at it. But that does not seem to be the case.
What's the point of finding the end of pi then? What is it?
I don't think we're looking for the end of pi. I think it's just like always learning.
So like all it's gonna be is 1, 2, 3.
Right?
But we don't even go through the numbers that are like the billion numbers after that. We just go through the.
Oh, so like why do I teach you pi?
No, like why are they trying to find more numbers to pi if we literally only learn?
Because maybe there is a repeating pattern. Maybe we haven't figured it out yet.
We have more problems to worry about, like global warming.
Don't worry, they're working on that too.
Global warming is insane.
Okay, so, anyways, so we need a way to deal with all of the other square roots that are out there. And the reality is that we could say, okay, let's say I want to talk about the square root of 8.
2.
Okay? And the square root of 8 is an irrational number. So I could plug it into my calculator and I could get an approximate decimal. I could do that, right? The problem is that these types of radicals show up frequently when we are dealing with triangles. Right? You'll learn a lot more about when they show up if you take more math. It's not super important right now, but triangles are really important in the structure of a lot of things. Right? Like if you think about bridges, we use triangles to support the weights.
We do.
A house often has triangles for the roof. Trusses? What are these called?
Roof? I don't know.
Trusses? I think maybe it's a I don't know.
Triangles.
Okay? There are lots of triangles used when we are building things. Now, when we actually design a bridge, a house, a large building, we don't actually come up with a plan that's so big we unfold it and it's 4,000 feet long. Right? We design it super teeny tiny and then we blow it up. Right? We make a scale model. So if we round the square root in the scale model and we're only off by 1/10 of an inch, we might say, oh, no big deal, we're only off by 1/10 of an inch. But then we multiply that by 1,000 to make it the actual size. Well, now we're off by a foot. Is that going to be a problem when we go to cut the beams if we're off by a foot?
Yeah.
Sure is. Okay, so we need to be able to deal with numbers in their exact form until we are ready to have to round. So today we're going to talk about how can we deal with these square roots in their exact form in the simplest way possible. Obviously, we are not going to continue to talk about a number of the square root of 25. We would turn that into 5. So the same thing is true for any type of square root. Okay, now, when we are simplifying a square root, what is really happening is we are really looking for a perfect square that divides evenly into 8. Okay, and we should agree that the square root of 4 is what? 2, right? Square root of 4 is the perfect square. So I could say that this is really the square root of 4 times 2. And I know that the square root of 4 is 2. The problem with this is that what happens if I say, okay, let's simplify the square root of 2,526. Being able to think of the largest perfect square that goes into that square root, now all of a sudden isn't as simple. So we want a process that's going to allow us to simplify all square roots, whether it's a number, whether it's a variable, no matter what, and get it in its simplest form without doing a decimal approximation. Okay? So let's say we wanted to simplify the square root of 40.
20, or not 20.
The square root of 40 is not a perfect square,
It's 10 and 4.
right? So here's the thing. I think some of you are going to be able to see perfect squares within them, but I don't want to have to start with the square root of 2,560. Okay, so I'm going to give you the process going through. The first, no decimal approximations. First thing that we are going to do is we are going to prime factor. Okay, so we are going to take 40 and we are going to prime factor it just like we talked about when we were factoring 2 weeks ago. So what does 40 split into?
22.
You could pick 4 and 10. You could pick 8 and 5 as long as you are picking mathematically correct options. What does 20 split into?
10
2 and 10.
2 and 10.
Yeah, get right.
What does 10 split into? 2 and 5. Okay, so 40 now prime factors into 2 times 2 times 2 times 5. Okay, that's step 1. And we should already be able to prime factor, so that shouldn't be an issue. Step 2. We are going to circle any pairs that we find. Now, one of the reasons why I like this process, I'm using pairs a little bit loosely here, because it works for any type of radical. We are mainly going to be focusing on square roots, but if it was a cube root, you would circle any triples. If it was a fourth root, you would circle any quadruples. Okay, so it works all the time no matter what the number is. Okay, so we're going to look up here and we're going to look for any pairs. What do we see a pair of?
2.
Okay? If there's more than one pair, you can circle more than one pair. Here's going to be my really fancy math words. Circled stuff. There really are words like the radicand and things like that, but we're not going to get into it.
Radicants?
Radicands, yeah.
Circled
The circled stuff, whatever we circle, is going outside.
Don't send it outside.
Okay? Whatever we don't circle is going inside. Now, here's the key. I have 2 shoes, but how many pairs?
3.
One pair of shoes. Right? There are 2 of them, but they count as 1 pair. So these 2's count as 1 pair. So when I pull this outside, it counts as 1 pair. I'm only writing it down 1 time. Yes, Haley?
So we wouldn't sound dumb. We wouldn't sound dumb, but teacher asked us, so how'd you do this? And then I was like, well, these are pairs, and plus the circled stuff, and they're like, circled stuff, so
Yeah, no, they know what you're talking about.
Okay.
Okay, then this stuff that's not circled
Guys on the inside.
goes on the inside.
So 2 and 2 divide.
So 2 and 5 are going inside.
So
Anything that is in the same location gets multiplied together. So all the outside stuff gets multiplied together, and all the inside stuff gets multiplied together. Okay, so 2 is outside, 2 and 5 are both inside, and we get 2 square root 10. Yes, Billy?
So if we had like 2 pairs of 2's, would it be 2 squared on the outside?
No, we turn that into 4. We multiply that.
Wouldn't that technically be 6?
Yeah, but you don't want to write 2 squared. You want 4.
Where'd you write
Say it again. No, this doesn't have a 4 in it. Okay, now, if you pick up your calculator and in your calculator you put in the square root of 40. So do second x squared 40 equals,
6.3.
6.3.
okay, we get that big long decimal. Okay, now clear out your calculator and now do 2 second x squared 10.
Same thing.
We get the same thing. These are the same values, but in a simplified form. It's just like we wouldn't say 4/8. 4/8 is 1/2, but we would write down 1/2. You don't think about it anymore because you've been doing it for so long that you just know you should reduce a fraction. Square roots and radicals are the same way. We should just get it in its simplest form. Okay. Let's say we wanted to simplify 756.
What?
325.
X to the third. Now, this is the exact type of problem of why we have the process. Okay? Because I can't tell you off the top of my head the largest perfect square that will go into 756. I would have to start listing my perfect squares and dividing them in and finding them out. Okay? It is way quicker to just start prime factoring. Okay, so if I start prime factoring, what goes into 756?
2. Yeah,
2. So right, we could take 756 and divide it by 2. Just face the front.
378.
Just turn around and face the front. Turn. This isn't really a choice.
What do you mean I'm facing the front?
I want you to turn and facing the front of your desk, please. So that we can all just like move on with class and not have other distractions.
I got distracted, I'm sorry.
Can we handle being here today? Yeah, so it's good. If you get a pass from your folder. You don't have any more passes left? We'll discuss when we get through notes, when we finish notes first.
I kinda gotta go now.
Go quickly.
What is that?
Funny.
You sound like a chainsaw story.
Okay, so we divide by 2 and we get 378.
And then 3 and 1 6.
Okay, so then we'll go to the 378. What do we know will go into 378?
2. 3 goes into that?
2.
I was about to say.
What were you about to say?
189?
What goes into 189?
3, maybe?
Do we know how to tell if 3 goes into a large number?
No.
Add up all the digits. What's 1 plus 8?
9.
And what's 9 plus 9?
18.
Is 18 divisible by 3?
Yes.
Yes, then 189 is divisible by 3.
I was right, bro. I'm so smart. Never been mean to you personally.
Stop.
So when you put it in the thingy, would you put 3 and 2 on the outside?
Well, hang on, because we're not done prime factoring yet.
Or not?
So now we have 2 times 2 times 3 times 3 times 3 times 7.
A lot of numbers.
But I'm not done prime factoring because I still have the x to the third power. And what did we say this would prime factor into? X times x times x?
Is that the answer?
Do we always have to multiply?
That's it prime factor.
Do we always have to like divide like 2 halves? 2 numbers?
No.
Like 3 and 7?
That's what I'm saying.
You need to get it divided as far as you can go.
So,
No, but I'm saying like, you know how you do 2 times 2 times 3 times 3 times 7?
Square roots.
How come you did all the corner and then you did the 7?
Anything that doesn't have a branch coming off of it. So these don't have anything down here, so it counts. Doesn't matter where it is in the pattern. Charlie, just
What?
don't talk.
What?
Because I asked you not to. It's how we're respectful in classroom and we act like students.
I'm talking to you about
I-
a problem.
You're not.
I could have been.
Okay, so now we're gonna look for pairs. What do we have pairs of?
3 and 2. So 12.
Okay, so anything that we said was a pair, we are going to put in front of the square root sign. So this counts as one pair. So a 2 goes in front. This counts as one pair, so a 3 goes in front.
Is it time?
This counts as one pair, so an X goes in front. And anything in the same place gets multiplied.
why did you
How?
put 2
I
x
did
to the
square.
third in front instead of putting the multiple? writing it.
I mean, this doesn't have an exponent of 3 with it. This pair just counts one time.
No, but like just the 2 has the like what if you wrote 2x and then 3 in front?
You can put 2 times x times 3.
Well, why do you have to? Okay.
Each pair counts one time and it's being multiplied together. These 3 things are being multiplied.
Wouldn't it be 9 is getting multiplied?
Okay, then we're gonna go inside. So left inside we have a 3, we have a 7, and we have an x.
So I have a question. Why do you have to why do you have to do so much work for that?
I mean, you have to find the largest perfect square that will divide evenly into it. Then we're gonna multiply things that are in the same location. So this becomes a 6x. And this becomes a 21x. Bailey, don't talk. Stop. Yeah, not really sure how notebook checks are going to go today when some of us like don't even have a notebook out. So what's the first thing that we're going to do?
Prime factor.
Okay, so 2 times 10. 2 times 5.
There's one pair.
So this turns into 2 times 2 times 5. Okay, so what do we have a pair of?
2.
2. Okay, so don't. Not appropriate, ever.
What?
Just go out in the hallway for a minute.
What did I do?
Go out in the hallway for a minute.
Shut up.
What number are we pulling in front?
2.
What number stays inside?
5.
Okay, now we still have to consider one more thing because what number was already sitting out there?
4.
Okay, so remember numbers that are in the same location get multiplied together.
That would be 8.
So it'd be 8 square root 5.
Wait, what?
Okay, and you can always check, especially when there's not a variable, because you could put your calculator 4 square root 20 and get that decimal approximation, and then type in 8 square root 5 and make sure you get that exact same decimal approximation out.